So I'd like to start by saying well done for getting here first thing in the morning after the party last night, if you were there. I'm sure they put this particular talk on in the graveyard shift on a Saturday because of the title. We'll get to the title in just a moment. But first of all, I should introduce myself. I'm Phil Nash, known to many here. Developer advocate at JetBrains, which means I talk a lot about our C++ tooling, CLion, ReSharper C++, and app code for now. So feel free to come and talk to me about that afterwards or at any time. That's what we're going to talk about today, though. So, for some reason, my clicker, which is fully charged, has stopped working, so I'll use the keyboard. I want to start with a little bit of history, because this is not the first talk that I've done on error handling with a pun in the title. We'll get to that in a moment, but this talk is about this paper that you may be familiar with by now, especially if you went to Herb's keynotes earlier in the week. So P0709, now R2, is the paper. So although we're going to be talking about the same topic, we're going to cover some much different material to what Herb covered earlier in the week. And so it's not the first talk I've given about this. I've been doing this one for most of the last year. Optional is not a failure. Who's seen this talk? So a couple of people. So I'm going to review some of the material from that as part of this. So if you're not familiar already, I should bring you up to speed. Now, funnily enough, this was not the first talk that I gave with that title. Earlier in the same year, I did this one at a Swift conference. There's a story behind the title slide, by the way. This is at an iOS conference, App DevCon, and I was talking about Swift because Swift error handling actually is, I consider one of the richest, most fully featured error handling strategies of pretty much any language today. And that was not true when Swift first came out. Swift 1 came out in 2014. Basically had no error handling strategy beyond error codes and out parameters. Although it did have a very well-supported optional type in the language. So a lot of people were using that for error handling, including sort of built-in Monadic support. But it didn't have anything like we have with exceptions or anything like that. And then with Swift 2, when that came out a year later, it actually came with this fully fledged error handling mechanism that they deliberately didn't call exceptions, even though it looked a bit like it. And it's based on my experiences with that. Well, first of all, when I did this talk, the main purpose was to show how what we call Swift error handling was actually, you can trace it directly back to monadic error handling with result types. So we'll get more onto what that all means a bit later. But I was trying to bring that out. So then I submitted a talk with the same title to a C++ conference, C++ Now, last year. And my intention at the time was to just present current error handling strategies from error codes and exceptions, of course, through the ADT stuff that we'll get onto. And then even sort of Monadic Binding that we might be able to do in the future, to what could we do if we actually change the language to better support this? Where could we go with this based on what I'd seen done in Swift? That's what I wanted to talk about, get people thinking. But then I came to the ACCU conference last year, and we had an SG14 meeting, just in a room around the corner, where Herb presented for the first time P0709. And I immediately recognized that it was talking about exactly the same thing. So of course I changed the talk to incorporate that. It still did all the different error handling techniques, built up to right at the end, just in the last few minutes, introducing that paper. And of course got loads of questions about it. So this talk is a follow-up to that, where I'm going to go much deeper into the paper itself and some of the supporting papers and what it really means behind the scenes. So it's much more nuts and bolts implementation. But I want to continue on this history theme just for a moment, just to emphasize that this has really been a convergence of different people's thinking on error handling, not just in C++, but in multiple languages. And for me, my interest in alternate error handling strategies probably started with exploding return types. So, who's heard of exploding return types? Few people, but not everyone. They're really a thing. Who's actually used them? Just me? Okay. So, yeah, I experimented with exploding return types. And I think when I first heard about them was a talk from Andrei Alexandrescu at the ACCU conference in 2007, Choose Your Poison, Exceptions or Error Codes, where he claimed that actually we could get the best of both worlds. And that's what got me thinking. And one of the slides from that talk, this one, if you read it through, it actually reads much like the sort of result type that we're going to come on to. But here's the interesting bit. The destructor throws an exception if you haven't checked whether it had an error or not. So it forces you to actually check whether there was an error, even if you don't actually need the value. If you don't, it throws in the destructor. If that sounds bad, well, it is. But the point is, it's meant to make you discover early whether you're not paying attention to your error handling strategy. And that was a bit that I liked, and actually used it quite successfully for a few years. Bear in mind, this was 2007. So actually, Andrei's interest in error handling techniques actually goes back to 2002 at least, again at the ACCU conference. This was the year before my first one, so I didn't get to see this talk, but he did a talk, Error Handling in C++. We're inching towards a total solution. And the last sentence there says, today the long evolution is reaching maturity, back in 2002. You can devise a complete set of rules and a reusable framework to implement error handling in C++. And apparently now in 2019, we're still not quite there yet. Maybe we're looking at 2023, 2026. But I think we are still inching towards that solution. But I actually dug even further back. And back in the year 2000, found this thread on complang C++ moderated from Ken Hagen, Exploding Return Codes. They seem to be where the name comes from. And you can see there the destructor throwing if RC is less than 0. And I like the start of it. Out of intellectual curiosity, likely story. So, interestingly, in the same thread, Lisa Lippincott pitched in, and I like her comment. Let's not repeat the mistakes of the past. Model the copy constructor and assignment on the current auto pointer, not the old broken one. Different times, eh? But it's interesting that Lisa weighed in because she was actually referenced as being prior art on this. She had something similar even earlier. And in James Cann's even earlier still, the reference later in the same thread suggested that his idea predated exceptions. So this idea of exploding return types has been around for a long time. And my main point here is that interest in alternate forms of error handling has been with us for a long time. Moving forwards again, but still continuing the history, back to Alexandrescu. In 2012, he did another talk, Systematic Error Handling in C++. And this one seemed to be a bit of an evolution of his likely type that we saw in 2007. A slightly more refined idea of a type that can contain either a value or an error, and then a means to distinguish them. And if you try to get the value out without checking, then that will throw an exception. And the idea is that it holds the exception type. So that part's still there, but not from a destructor this time. So no more exploding return types. What had changed between 2007 and 2012? Of course, we now have C++ 11, which makes destructors no except by default. And my own implementation broke around that time because for some reason, because of our hierarchy, I couldn't actually make it no except false at all. So I had to change the design. It's probably a good thing in the long run, but it served me well up to that point. What's interesting about this type, though, is he actually calls it expected. If that sounds familiar, it's because stood expected is currently going through the standardization process. Quite an advanced stage now. It's R7. not adopted into the standard just yet, as far as I can tell, but still on track to. Stood expected is based on boost expected, which is based on Andre's expected. So slightly different, but same basic idea. So a question here.
Why not just exit?
Sorry?
Why not just exit?
Why not just exit?
Yeah, instead of throwing an exception.
Well, that's what James Cairns' implementation did, obviously before we had exceptions. And I think it's only really recently that we're starting to get a clearer idea of which things should actually abort and which things should be handled through something like an exception mechanism, which, given how much time we've had of these things, is a little surprising, but we're just starting to get more clarity on that. And I would agree with you now that aborting would be the better answer, because it is a logic error if you haven't checked your error handling. If you're meant to do control flow error handling, then you should have checked it. So, very good point. Back to expected though. This still has the same property where if you do try to check it and it's an error, then it refrows it. So we're not quite there yet. Although there's still time to change that, of course. But this is not a unique thing to C++. In fact, just a handful of languages that I know about, starting with Haskell, has the slightly more general either type. Can be either of two values, and if you use it specifically for error handling, the second type is usually the error. Rust has a result type, Kotlin almost identical, Swift and F#. Interestingly, Swift, I mentioned Swift earlier, having a very complete error handling strategy. It's only just got the result type. In fact, because of what Swift error handling does, it doesn't really need it unless you actually need to store the result in an intermediate form, perhaps for async. So it's got it for that purpose now. But we could actually build our own before that. But lots of languages, I mean, this is obviously not a complete list, do something like stood expected. This idea of holding either the value or the error in a very compact way. So how do you use these types? Let's have a look at how you would use stood expected. So in this example, it's just a very simple function to convert a string to an integer. Don't worry too much about the implementation. That's not the important point here, it's the error handling. So as you can see, it's returning a stood expected. By the way, I favor trailing return type everywhere. Don't get put off by that. Returns a stood expected of int or stood domain error. So the actual type we're interested in is int, and the error type stood domain error, because why not? Probably come up with a better one, but the point is you can put anything there. In the case of an error, we return stood make unexpected of our domain error. The make unexpected part is just to make sure that if the value type and the error type are convertible between each other, we don't get an ambiguity. This always constructs the error type. And that way then in the success case, we can just return the value, and that automatically constructs it with the value. Simple as that. If we just put that up there, we can actually have a look at how we would use it, and it is pretty much as you would expect. So this is the happy path. So we call our parser function. We get a result, which is our stood expected. We can check the result with the Boolean operator, which works as you would expect, much like a pointer really. You can dereference it as well. Very similar to optional, except that in the failure case, we can now get an error message. So .error gets us our error object, which in this case is a stood exception-based type, so we can call .what on it. Obviously, whatever the type is there, you can do whatever you want. But the interesting bit is the fact that the highlighted part is the happy path, and everything else down here is boilerplate associated with the error handling. So it's quite heavyweight. And actually, this is an optimistic case. Just to contrast, that's the error path. If we actually stack up a couple more functions, now like this one, to divide two integers, again returns a stood expected, so it could detect division by 0. Again, it's just for the sake of our example. And then one more, another function just to add 1 to an integer. No std expected this time, it's just a straight function. If you want to compose those functions together, you have to write something like this. Now that's getting quite messy and ugly. Lots of nesting there. So just to run through, so we're parsing the integer at the top, we've got to capture the first result. We've got to do an if on that. If we have a value, then we can dereference it and pass it on to divide. Get another result. We have to check that. If we have a result there, we can dereference that and pass it on to add 1. Otherwise, we've got all these else's to handle the error case. Now, you might say, well, if we use early returns, that can clean this up a bit. And it does, but it's not that much better. I mean, this is still lots of code, lots of boilerplate for handling the error case. Now, there is something else we can do, actually. And I mentioned earlier about monadic binding. We're not going to get into the sort of mathematical underpinnings of what that really is, but you probably know by now that it usually involves these map and bind functions, and in this case, map and then mean the same thing. These are not on std expected yet. There's a proposal to add them to std optional, which is going through quite nicely, and that will probably go into std expected later as well if we get that. So this will probably be coming. So you'll be able to do the same as we had on this slide. We can achieve like this, which I think you'll agree is a lot less code at least. And once you get used to the extra syntax for the lambdas, I think a lot cleaner. There's no manual dereferencing, no checking of error states. The code you actually write within that just assumes that everything already has a value and there's no errors. But what you're actually returning here, or getting out at the end, is still a std expected. So you can just collect all of your error handling to the end. So it's starting to sound more like exceptions, actually. You collect your happy path in one block, or sequence of blocks, and then the error path in another block. But even though this is about the best we can do with std expected if we add those monadic functions, the competition, of course, is exceptions. As we have them today, look how much less code that is still. Let's go backwards and forwards, because it's not just down here, it's the code at the top as well. It's a lot less. So it's quite a hard sell, I think, to get people to move to this. And this is sort of about the state of the art in C++ for error handling at the moment. It's not even in the language yet. So that's the problem. Now, introducing how we'll do it with P0709, just add a little bit extra so you can see the try keyword there. You can also see at the top the throws keyword coming in. So other than that, it's almost identical to exceptions that we have now. But here's the interesting thing. The semantics are basically this. So we get this, but with this syntax. I think that's a really important point here. And in my previous talk, optional is not a failure, I go into quite some length why that's significant, particularly for performance reasons. So I'm not going to cover that ground again too much now. But that's really the clincher. So let's dig a little bit more in this. So bringing back the parsing an integer function that we had earlier. Let's have a look a bit more closely. So here's the important moving parts. The throws keyword qualifier at the end of the function, where we would normally have no except. Throws is new. This is the magic, because this is what makes the whole function opt in to what we're calling static exceptions. They're called static exceptions not because it happens at compile time, but because there's no dynamic allocation. It's all using values. In fact, the title in the paper is throwing values. And here we can see throwing stood error C invalid argument, that is a value, and we'll actually look at the type in just a moment. So no dynamic allocation here, and we can't see here, we'll see in a moment that we can catch by value as well. The other point here is this try keyword that gets added. This is actually an optional part of the proposal. I think it's a very important part, and we really should try to get this in, because between that and the throws keyword, this solves another big problem with exceptions as we have them today, which is the invisible control flow, and Herb alluded to this in his keynote. I think this is a really big deal. Now, the throws keyword, this try keyword here, the underlying mechanism, this is all pretty much identical to Swift error handling, which is why I brought that up earlier. We've now had 4 years experience in Swift with this mechanism. It's working out really well. So different language, some different other semantics and properties, so not directly comparable, but they're close enough. This gives us a pretty good idea that this can work really nicely. And no one's really complaining about this try keyword. Some people are complaining in the C++ world, but certainly not in the Swift world. All right, so concentrating a little bit more on the bottom, rather than just some code on its own, let's put it in a function. So this is a function that's representing the composition of these other functions. So you can see that we need to put the throws keyword here as well, because we've got the try keyword there. If we don't put one or the other, that's a compiler error. It's all checkable at compile time. So unlike no except, where it's only checked at runtime, although there's a compile time element to it, of course, this can all be verified at compile time to make sure you're doing your error handling correctly. Question again at the front.
Say something to do with that string stream through an ordinary exception. What happens there? Where's the flow going?
Sorry, say it again.
That string stream operations,
Mm-hmm.
they could perhaps throw an ordinary exception. Where's the error flow
Right.
going there?
So the question is about what happens if the string stream throws an ordinary exception. We will come back to that a bit later, not in this specific case, but there is an interoperability story there for moving between the classic exceptions world and the new exceptions world. We will come back to that later, but it is there. But yeah, good question, thank you. So, yeah, so this becomes a throws function as well, which means callers of this will need to do the same thing, and it's try and throws all the way down. Other than that interoperability story we'll come back to. Sorry, that's just the highlighting. The color scheme here is just to show the yellow highlighted blocks are the new keywords. Although we have try blocks now, this is a try keyword, it's different. Whereas the throw keyword is reusing the existing semantics, but with a slightly new meaning when you're inside a throws function. Okay, so this was returning or passing on the error. We can, of course, use try catch as well to catch the exception. And notice, as I said, it's by value. It's this stood error type that we're going to dig into a bit more in a moment, but we're catching by value, so this is a change. With classic exceptions, we catch by reference, or we should, and that's part of the problem, because that's opting us into needing to use RTTI to actually be able to catch the different types. Even if you're only catching one type, you're still using RTTI for that. So we've got the dynamic allocation and the RTTI. That's the big problem with exceptions. This bypasses all that, because although this looks very much like legacy exceptions, as I said earlier, this maps back directly to that ADT style error handling we stood expected. Question, Martin.
Why does the print function use throws? It doesn't look like it's throwing, it's not rethrowing an exception.
This is an area that I think might need some clarification, but my understanding at the moment is you need the throws keyword there just to opt you into the new syntax. So the try and catch has the new meaning as opposed to the old meaning. And that may evolve, or I may even have not quite got that right, but that's my understanding at the moment. Yes?
This is a void function, and if I understood correctly, the throws basically
Mhm.
And so since there's a void function, so return something of either an instance of void
Mhm.
or an error or kind of unit type.
Yep. So your point was that the throws keyword, like I said earlier, it's like a mechanical translation back to a function using stood expected. You can do stood expected of void, but in this case you're not actually propagating the error out because you're catching it. So that's your point. And when I was putting this slide together, I realised that there is a loophole there, and I wasn't quite sure what the solution was because, so my understanding is without the throws keyword, our try and catch here will have the old meanings. In other words, they're going to be expecting an RTTI-based dynamic exception. So there may be some other mechanism that I've missed so far that lets you opt in. So don't take that as the final word on this. But in general, when you see the throws keyword, that means this function uses new style exceptions. So just to emphasize what I was saying about this mapping. So the throws keyword, and there we have an example with a void return. That maps to a return of stood expected of what your return type would have been. So if we're actually returning an int, it's going to give us a stood expected of int and stood error. Now this is not a literal translation. This is an as-if translation. It's up to the compiler exactly how that implements it. And in fact, it gives it scope to optimize it even further, which we'll discuss a little bit later. But you can think of it this way. So throwing one of these values is as if you are returning a stood make unexpected of that value. And then the try keyword, that little try keyword that people are complaining about typing those 3 characters for, gives you all this. These map and then monadic binding functions with the lambdas and everything. All of that's unwrapped and you don't have to worry about any of that. And yes, technically you could do the whole thing without the try keyword. We can still do that, but then you lose that traceability. So I think that's a very, very small price to pay for everything you're getting there. So going back to this code. Been skipping over this stood error bit, because this is also a really important part of this. As we said, it's a value type, and that's what makes this all work. But the definition of it is actually in a separate paper. This is P1028, currently at R1. So it's actually talking about status code and standard error objects. Notice for P0709, zero overhead deterministic exceptions. So it's right in the title. It's saying this is a supporting paper for the main exceptions paper. But don't let that mislead you. This is a fully fledged standalone proposal that has a lot of value in its own right, as hopefully will bear out. And just to read a bit from the opening paragraph. A proposal for the replacement in new code of the system header system error with a substantially refactored and lighter weight design which meets modern C++ design and implementation. And we're going to dig into this a little bit now. But who here is familiar already with system error? Yeah, not many people are using it. It's been in the standard since C++ 11. It's an integral part of the file system API and the networking TS. And it's just very misunderstood and underused because it's incredibly useful. And we'll actually just summarize exactly what that is in a moment. But just come back to this. So what we're going to be talking about here is stood error. But we're just going to take a little aside and talk for a moment. Oh, before we get to that, sorry, I forgot this slide. This is what stood error actually is. It's actually a type def, effectively, for this thing. So it doesn't look as simple as we might like. Actually, it is. We'll fully define that towards the end of this section. Right, here's where I thought we were going. Stood error code. So we just looked at stood error. That's the proposed one. Stood error code is what we currently have in the system error header. subtle differences in names can catch you out if you're not familiar with them. So just to emphasize. So now we're talking about what we have in C++ 11 and on, because this is our starting point. So this is a simplified sketch of what std error code actually is. Basically just an integer and a pointer. So quite a small type, can fit in 2 registers, that's important. The integer actually is a stand-in for any enum. And it's an integer because it can take any enum, not a specific enum. So that's important as well. It's effectively type erasure for enums. And then the pointer to an error category is what gives that undefined enum meaning. This is effectively the context or the domain for that set of enums for an error code. So the default domain is this, basically the POSIX error codes. So there's an enum for that. And then there's an error category for that. So the error category knows what the enum is and then can do something meaningful with it. And we'll have a look at that a little bit more. But let's go on to that now. So just to expand a little bit more, here's some of the methods in error code. Again, it's not complete, but we just got a couple of excesses, so you can get the value and you can get at the error category as a reference rather than the pointer, but otherwise they're just straight accesses. So they're obviously important publicly. And then, oh, I was going to drop down. So the other methods there, message. Where does that come from? It's not actually holding a string anywhere. That's interesting. And a Boolean operator. We'll come back to that, I think. Just talk a little bit about the error category. So here's an example of a custom error category. It's got quite a few methods, but here's the most important ones, I think. A couple of methods called equivalent and message. We'll talk about those in a second. Down the bottom are some examples of some error domains. So you have an enum. Here's the default one based on the POSIX error codes. So you probably recognize the actual POSIX names there, and then just the enum names they map to. And then over here we've got some custom one that's associated with our new error category. We could put anything we want in there, no matter how silly they are. Now all these lines look a bit confusing. This is all talking about this equivalence stuff. So there's 2 ways that you can compare these error codes. If you compare one std error code to another std error code, you are just doing a direct exact match comparison, just as you would expect. So it must have the same enum value and the same error category, which is useful and it's what you would expect. But what's really useful is the ability to do a semantic comparison. And that's where this equivalent stuff comes in. You see here, these lines here, we're saying, well, this error code can potentially match one or more of these error codes and vice versa. And I need to apply a mapping there that's one-to-one, one-to-many, many-to-many, whatever makes sense for your error category. And this is really useful because when you define your own error category, that might map to some standard error codes, but not necessarily in a one-to-one way. Be able to do that mapping and be able to say, okay, I've got an error of my custom error type, but I'm just going to use POSIX error codes to try and do something about it. That's what lets you do that. Unfortunately, in order to achieve that, because if you just do an equals comparison between 2 error codes, it gives you the exact match. We need a separate type to do the equivalence comparison, and that's this error condition up there. I didn't do a highlight on it. But you can see in the first equivalent line, it's an equivalent between an int and an error condition. Error condition is almost exactly the same type as error code, but it's just a separate type so that we can do this. So we can do these overloads. A little bit subtle, a little bit confusing, but it is really useful. So ideally, we want to preserve the useful part and lose the confusing part. So I'm not going to go too much more into that because this is old stuff, but Right, so finally, yeah, I thought I had a slide like this. So now the message here on the error code, we can see how we can get that because it forwards on to message on the error category that we saw before. That's up there, shakes the error code. So when you provide that error code integer to the error category, it can then statically, effectively, usually with a big switch statement, just map that code to a string and return it. So it doesn't need to store those strings anywhere, which is really nice. So the problem we have with exceptions at the moment is a lot of them are just carrying strings around. The same strings everywhere. Most of the time, we very rarely use the ability to dynamically construct a string. So this just gives you back a string version of whatever the error code is. It's quite nice. Unfortunately, the Boolean operator is not as useful as it sounds. The way you want to use it is to say, does this error code contain a failure or not? It's not actually what it does. What it actually does is just tell you whether value is all zeros or not. Sometimes that means it's success or failure, but there's no guarantees, which means it's almost completely useless, which is a shame. So there's that problem as well. I say there's lots of other methods. They're the important ones for our purposes now. Let's just summarize the issues with std error code. Remember, this is what we have in C++11. There's an implication that those categories, remember holding them by pointer in the std error, they must be singletons. And in fact, they are, all the standard defined ones are singletons, because their identity is their pointer value. So when it does a comparison between error codes and it compares error categories, just comparing the pointer values, that's how it's actually defined to do it in the standard, which is convenient, and most of the time does what you expect, but there are problems with that, particularly for header-only libraries. If you have a header-only library that defines an error category, and then you have that included in more than one dynamic library, for example, you're going to get separate instantiations of those singletons. They're going to have different pointer values, and then they won't compare. So again, it's not quite doing what we wanted. So that's the first problem. Ralph?
Ditto that point across process boundaries and promoting. This serialization would be interesting.
So you're saying, yeah, you get the same problem across process boundaries and beyond, which is true. That's not really an issue here because this is only meant to be within a process, and I think you would need some other way of serializing that. But good point. And in fact, the solution to this should also solve that problem. Possibly, actually, I'm not sure now. We might revisit that. Anyway, the next problem depends on std string. Doesn't sound like that big a deal. Everyone uses std string, don't they? But yeah, because we've got that message method, which returns a std string, which is the only string type we already had in C++11, std string depends on allocators and ostream, std ostream, and various other big headers that have their own dependencies, locales. You're putting in all the locales for something that is often used in really constrained environments where they want to use error codes instead of exceptions. And we're opting them into all of this extra dependencies. So that's actually a big problem for a lot of people. Maybe not everyone, but it can hit compile times and it can cause problems. So it's a shame when all you really want is just the ability to get a string. We mentioned about the bool conversion not really being reliable. It's almost completely useless. And we mentioned that the need for that separate error condition type so we can do the semantic comparisons can actually be a bit confusing and nuanced. A lot of people, even in the standards committee, apparently still don't quite get that. Also, it's not const-expr. It's not too surprising. Const-expr was pretty limited in C++11. And there wasn't really such a big push to const-expr all the things. We can do better today. But those singleton categories especially are a big obstacle there. And talking of categories, when we defined what they were, we said, well, it's like a domain. That's usually how people describe them. So why didn't we just call them domains? Not a big problem, but it's another little nit. So this is what what's proposed in the new paper. This is status code. So we were talking about stood error. So why are we talking about status code? Well, this is the generic part. See, it's a template. So this is more general than stood error code. But otherwise very similar. You've got a pointer to a domain. It's actually called a domain this time. Brilliant. So that's the equivalent of the category before. And then it has a value, which now is a template type. So we can put anything in there. And we're going to specialize that in a moment for use with error codes. But on the subject of the domain, although it's a pointer, that's now not its identity. So you can have multiple domains or multiple pointers pointing to the equivalent domain, and they will have inside them an integral ID, which is initially assigned as a random 64-bit number, I believe. So even if different dynamic libraries have their own instances, they should have the same ID, and therefore will compare equal. So that solves that problem. All right, let's dig a bit more. So we saw this earlier. This is stood error. It's actually one of these. That still doesn't map to that. Status code doesn't appear there except as part of this errored status code. So what's all that? Well, errored status code is another parallel type. So it's like status code, but it's guaranteed to never contain an error. So we saw earlier, error code maps to things like POSIX codes, which has some success codes. Sorry, did I say never contain an error? I meant never not contain an error. Will always contain an error. So in general, those error codes include success codes, or sometimes success with warnings codes. But what we want here is only to contain error codes. And it does this by checking it in the constructor. So potentially you can get a failure at runtime. For our purposes today, that's never going to be a problem. It's always going to be constructed with an error. So that's what you want. So it will always be an error code, never a success code. That's what that means. Otherwise, it's the same as the above. And then you have this erased bit. So now we're supplying the argument to the template above, the thing that's going to give us our E. So this erased, obviously to do with type erasure. That's exactly what it is. It's a little helper template to type erase something and put it in the storage that you pass as its template parameter. So here we're using system code value type. Just to explain what that is, system code is another template, but by default, its value type is int pointer t, which means that, unwrapping all of that, erased is going to be something that's type erased, but stored in an int pointer t, or the space of an int pointer t. So it will be that size. And that's going to be our E up there, which means, when you add all that up, it's effectively this. So our error, without a template type, has our domain pointer, as before, and something the size of an int pointer t is going to store our integral value, which is going to be our error code. So it seems like a roundabout way of specifying what we had before, with less of the problems, but it's actually part of a more general solution. So that's why we have the type erase stuff. Plus this bit about it's never going to be a success code. So just to summarize how stood error solves pretty much all of the problems that we saw before. Well, domains are called domains, little thing, but it's nice. Those domains are based on random int64 IDs, so we don't have the problem across dynamic library boundaries. Because it's been designed from the ground up as modern C++, and we don't have the problem with singletons, it's now mostly context-aware, which is nice. It doesn't have a string dependency. We didn't really look at that, but the proposal as it is now, bear in mind, this hasn't actually gone through the committee yet, so it may change. This part probably will, but rather than depend on stood string, it has its own string ref type, with good reason, but that probably won't go through. It's probably going to end up as a string view, but the string ref has some reference counting properties, and it's It's interesting. But it does mean that it doesn't have any dependency on std string, so that's nice. Doesn't have that Boolean conversion, because that never worked anyway. And for our purposes, it doesn't matter anyway, because it's always going to be an error code. We don't need to check it. If we've got it, it's because we had an error. And then the comparison is always equivalence. So it's never going to do an exact match comparison. And that means we don't need a separate type to disambiguate. So we get rid of that confusion. 99% of the time, what you actually wanted was the equivalence comparison anyway, when we're talking about error codes. So that actually turns out to be fine. One more thing here is, because this is a new type, but we already have std error code. There's code out there that uses it, file system API, networking TS. There's an error domain in std error called std error code, or error code, which contains a legacy std error code, which means in a way we have error codes for error codes now, but means beginning to operate at least. So with our effective std error, it still fits into 2 CPU registers as before, but more specifically, if a move of one of these types can actually be done using memcopy, then this can be extremely efficient. The compiler can elide lots of calls as a result of that. But we currently have no mechanism to indicate this to the compiler. So the compiler has to more conservatively call move constructors and things. So there's another proposal, another supporting proposal. P1029, currently at R1. Both of these supporting proposals by Noel Douglas, by the way. And in fact, this one is a very small proposal. And then there's a bigger proposal which incorporates basically the same idea. P1144 from Arthur Dwyer. Object relocation in terms of move plus destroy. It's a bit more ambitious. So I won't go into these in lots of detail, but just to put up the differences and similarities. So the move relocates one just defines an attribute where you indicate to the compiler that a move is the equivalent of memcopy. That's it. And that's just enough to enable the optimization for the purpose of error code, for the purpose of static exceptions. P1144 also has such an attribute, although it's an optional part of that proposal. And then it also has this other stuff. Particularly useful is the detection trait. So now you can say, is trivially relocatable? And if it has that attribute, or the compiler can prove otherwise that it's trivially relocatable, you can tell you that at compile time. And it also has some other things, like it can reset the moved from state, also using a memcopy. So basically the idea is, if you default construct one of your types and memcopy that over the top of something you've moved from, that gives you the reset state. And that's the definition of object relocation in this. So when it says in terms of move plus destroy, that's what it means. So it's 2 parts rather than just the one. And as such, it defines that relocatable concept. It's got some algorithms in there as well. They're not strictly necessary, not as interesting. But as you can see, it's a much more ambitious paper. So the idea is that, because this is going through at the moment, seems to be going quite well, but if that stalls, we can fall back to this one and still get what we need for the purpose of static exceptions. So, coming back to our earlier example now with static exceptions, this is what we saw before we got sidetracked onto the other proposals. That std error there. Remember, when we throw one of these, it's effective as if we are returning it inside a std expected, or something like a std expected. So we're returning something which is at least the size of a stood error, which is 2 registers big, now we know. It also needs to have something that indicates whether it's an error or a value, which you would think would just be a Boolean. In fact, because the compiler knows about this now, rather than actually wasting a whole Boolean on it, it uses a single bit in an unused bit in a register on the return channel that we basically get for free. So no additional storage, which means the most we're paying is the 2 registers in size to return one of these. And if there is a return value, it's usually going to be about that big or bigger anyway, which means if you're returning something, you're getting this in terms of storage for free. And the most you pay on void returns is 2 registers in size. It also means that when you're catching it, like here, that can map to an if statement on that bit. And again, because the compiler knows what you're doing, it automatically puts that on the sort of likely, unlikely path, which means branch prediction should give you back that zero cost performance of legacy exceptions on the happy path, and just the cost of an if check on the unhappy path. So that's where all the performance gains come from. That's why all of these parts are important. And that's why this works the way it does, and why it's not really been possible before now in C++. At least not at this level. So got through that a bit faster than I thought. That's actually the end of my material. But I've probably missed some things and you have questions. So any questions?